Okay, now it's recording. Yeah, okay. So yeah, again, before I start the session 6, I'll try to correct some mistakes from my past peer tutoring first. So it's in session 4. Yeah, it's under shear. Yeah, so all this is correct. Like all theory is correct, but what I have some mistakes, right, is actually here. It's when I'm trying to find ASW as which is the area of shear reinforcements per spacing. So my mistakes is, so first thing, this one should be 10 to the power of 3 instead of 10 to the power of 6. I got the units wrong. So this one should be 0.4679. Yeah. So yeah, I got this one wrong, but the steps are correct. The steps are correct. Also, this table is actually table for slabs. It's not table for shear reinforcement. So again, this is my mistake. So after getting like 0.4679, right? You actually need to go here, the shear reinforcement table. So in this case, you can check. Yeah, 10 millimeters diameter, right? 10 millimeters diameter links. Then ASW S is 0.4679. So you go to this table, then you check the 10 millimeters. So you can use anything actually, because like something like this, 300 spacing, 0.523 is, yeah, it's still bigger than this one. So you can use any spacing here. Yeah, but that's my correction for session 4, the shear reinforcements. Yeah, but besides that, I think nothing else that I want to correct. So I will upload this again, like the corrected solution in the what? In the OneDrive. So yeah, if y'all have the file already, you can re-download the file. Yeah, because I made a mistake here. Yeah. Yeah. So accordingly, I think this one. Yeah, this one is 0.24. Okay, it's not 240. Yeah, that's my blunder. Okay, so with that settled, I think we can go to session 6. Let me start sharing. Now session 6. Okay, so just to recap, last week we did what is it called? Quiz 1. Yeah, so we went through moment redistribution, we went through um, bending design for beams. Yeah, so today I'm going to continue with these two. So first things first, we have the SL stretch, and we have the slab design. But the slab design is just the intro. There's nothing much, right? Because I want to focus on this. Yeah, but even this is a little bit like tiny. That's why I added the slab here. Yeah. Just the intro. Yeah. So let's just start. By the way, I hope you all get your quiz well last week. Yeah. But anyways, let's start. Yeah. So just to start off, the one that we've been learning, right, or practicing is bending design and shear design. So if you notice, these two are ultimate limit states, meaning that we design it for failure. So there's bending failure and there's also shear failure. For today, we're focusing more on serviceability. So for serviceability, right, it's more to like um, comfort and also like how do we say it? It's more like, let's say you have a floor, right? If you want to put like something there, right? Of course, your floor cannot bend too much, cannot deflect too much, or else you cannot like put stuff there. Yeah, so it's deals more with serviceability, meaning that how can the building be used? Okay, so it's basically again it's functional use of the building, and then under SLS, right? There are a few actually. There's deflection, crack control, durability, and vibration. So deflection means basically how much the beam bends down. So this is the initial. initial position, then if you put it some load, right, it will deflect down like this. So there's a limit on how much it can deflect down. For crack control, if you, okay, let's say this is your cross section. If you put the bars too wide, right, or your bars are too small, cracks can form. So that's crack control. Then durability and vibration, I won't really cover it, but durability means how long can the concrete last? Vibration, yeah, basically vibration levels. There's a limit on how much the building can vibrate. Yeah, but for this course, we will be focusing mostly on these two only, deflection and crack control. Okay, then deflection, it can be affected by a few things: support condition, span, steel area, steel strength, and etc. You will see this in the formulas below. Then crack control, there's bar size and also bar spacing. These two. Again, we will see in the formula below. Okay, so let's start with crack control first. So for crack control, it's quite straightforward. We need to check two things. First thing is the reinforcement ratio. So if you see the formula here, and the vocabulary here, it's reinforcement ratio. It's basically how much do you reinforce divided by the area of concrete, quote unquote. Okay, so it's just A as provided divided by D times D. Yeah, so for reinforcement ratio, the symbol is rho. So there's a minimum limit and a maximum limit. So for minimum limit, you can follow either this, like this formula, or you can use table 6. So for each concrete strength, right, FCK, there will be a minimum percentage. That's like the lower bound of rho, or the lower bound of the reinforcement ratio. Your reinforcement ratio should not go below this value. Okay. Then for maximum, it's always 4%. So your reinforcement ratio, right, cannot be above 4%. Okay. So quite straightforward like, for reinforcement ratio. Then for flange beams, we use BW. So just to give you a little recap, so let's say this is your flange beam. So this whole thing is B, or sometimes people write it as breadth of flange. So these two means the same thing. Okay. Then this one is the BW. So it's the breadth of the web. So if it's a flange beam, we just assume that we only use this for deflection, BW. And so just put BW as the B here. Okay, so quite straightforward, nothing much to explain. There's a question later, so y'all can see how it's used. Okay. Second one is max bar spacing. So this one, it's up to you, or it depends on the question, whether they limit the crack to be 0.4 millimeters. So W here is crack width. Okay, so okay, let's say this is your concrete, right? Then let's say it cracks like this. So this is the crack width, right? Or W. Okay, so there's a limit also. So for 0.4, you can either limit maximum bar space, maximum bar size. So basically you limit the size of the bar, or you can limit the spacing. So maximum bar spacing. Yeah, so again, it's pretty straightforward. You just refer to the table. So that's for crack control. Yeah, there's nothing much to explain because these are like inside Eurocode 2, and you just need to follow. Okay, then second one, this one is a little bit more complicated. This one is deflection control. So the main formula that we're going to use is this. So actual L over D, right? It basically means so let's say you have a beam, right? So let's say your beam. So something like this. Okay, again, let's see the cross section. So if you were seeing the cross section, you're basically seeing it from this side, like so this like this small area, okay, something like this. Again, to review, there's the effective depth, which is from the top to the center of the tensile reinforcements. So this one is D. Okay. Then this is the support. Then we have this, which is the span. So for span is we label this as L. Then D is just this D, the one that we've been using for the past few weeks. So actual L over D, right? Basically, you just divide this with this. So it's that simple. Okay. So that's actual L over D. So actual L over D, you just divide this with this. Make sure the units are the same. So let's say this is 6 meters, right? And let's say this one is 600 millimeters. Then you need to do 6,000 divided by 600. So it's 10. Okay, so you must make sure the units are the same. So that's L over D, the actual L over D. Then the next one, if you notice here, you need to compare actual L over D with this. So first things, you have the basic L over D. So it's a term. Basic L over D is a term that I'll explain after this. Then you have three factors here, F1, F2, and F3. So let's go over it one by one. So basic L over D is like your basis. So the Eurocode engineers have done like a few experiments. Then they say like, okay, this is basically your limit. It's the basic L over D. Okay. So basic L over D can be found by these steps. So you find rho zero. So this one again, honestly, I'm not sure what this represents, but it's in the formula. So just plug in. Then you need to find rho. This is the reinforcement ratio just now. But the difference is this one uses AS required, while the one before uses AS provided. So if you remember the difference, right? AS required is basically, let's say you do some calculations, right? The bending calculations, then you will get one number, right? So that's AS required. Okay, and then you will, from the table, right, you will pick like some steel area that's AS provided. So this is just some recap. What's the difference between AS required and AS provided? Yeah, so even though both the symbol is rho, right? The two is a bit different for deflection and drag. So be careful with this. Yeah, and then just again, just follow the steps. If rho is bigger than 0.35%, use this equation. It's a very long equation. Otherwise, you just refer to table 5.8. So here's table 5.8. So this one is actually rho. So it basically says if rho is less than this value, then just use this for your span over effective depth. This one means L over D, basic L over D. Yeah, so this one is the case that rho is less than 0.35%. So if rho is bigger than 0.35%, you basically use this formula, the long formula. It's written here. So if rho is bigger than this, then use equations. Else, refer to table 5.8, which is this. This might be a little bit confusing, but it will make it clear when I start doing the question. I'm just giving you an overview first. Okay, then nextly, okay, first we have the basic L over D. So that's like the basis span, span over effective depth. Then we have these three factors, F1, F2, and F3. So for F1, it has something to do with the flange beams. So if you see here, there's BF divided by BW. Okay. So yeah. So F1 is basically a factor that accounts the shape of the beam, like T-beam or rectangular beam. Okay. Then the second factor is accounting the span. So for spans bigger than 7 meters, you need to plug into this formula. Okay. Or it's just F2 equals 1. Okay. So F1, F2 pretty straightforward. Then for the third factor, F3, you have this thing, 310 divided by sigma s. So if you look to the right, sigma s is this whole thing. Sigma s is sigma su, as required, is provided 1 over delta. Okay. Delta here is the redistribution factor. Is the one that we've been using since session 1. Okay. So this one is redistribution factor. Then you have this, which is as required, is provided. Then you have sigma su. Sigma su, you follow this formula. So again, it's like a lot of steps like. So Fyk is the steel strength. Okay. Then what's this? SLS divided by ULS. Okay. So for this, ULS is basically 1.35 GK plus 1.5 QK. It's our ultimate limit state load. If you remember, that load is 1.35. Live load is 1.5. For SLS, it's written here. So SLS design load is GK plus the trident. What's trident? Oh, psi. So this one is psi. Yeah, psi 2 multiplied by QK. QK is the live load. So psi 2 depends on the use of the structure. Is it for office or residential? Is it for shopping or area? Or for storage? So you just follow the values. Okay, so you'll get F1, F2, and F3, right? After plugging all the formulas, then you just multiply it with basic L over D, and you compare it with L over D. Okay, so this is our mean formula. But for some professors, they like to simplify to this. So actual L over D less than basic L over D times AS provided by AS required. So this one is less accurate and more conservative. It's because here, if you see the formula for sigma S, right? There's this thing, AS required divided by AS provided. So, and then if you plug it here, right? So F3 will become, it will flip now because it's below, right? So it's AS provided divided by AS required. So like this formula is like a simplification of F3. Oh, sorry. So this is like F3 but incomplete. So it ignores the delta, it ignores the sigma SU. It's just a rough estimate. It also ignores F1 and F2 if you notice. Yeah, so this is like a simplification only. Okay. So which two formulas to use? I will prefer to use the full formula because that's more accurate. The one above is approximation only. Yeah, but I'm putting it there because the two different profs, right, inside our course, right, they use those two differently. Yeah. So for our first half, right, which is the beam, the prof actually uses this one, the full formula. But then for the second half, the prof uses this, which is the approximate formula. Both of them are correct. It's just depending on the case. Yeah, but again, I would prefer the full formula because more safe. Yeah. Yeah. So let's just start with the question. So this one I'll put it into use so you get the sense of it. So this one actually from your tutorials also. So here we have a doubly reinforced rectangular beam. It has a continuous beam in an office area. Okay, it spans 10 meters, and then the ultimate limit state, this much steel is needed. And then we provide two number of 25 millimeters plus two number of 40 millimeters, which is this one that is provided. And then concrete class is C30. Steel bars are grade 500. Then GK over QK is 2. Delta is 0.9. Okay. So for the first step, check for the acceptability of the span divided by effective depth ratio. So this one is basically your deflection check. Okay. Let's put the words into context first. So let's say you have a multiple span beam here. Right? Okay, again, it's a continuous beam, office area, spans 10 meters. So 10 meters, let's say, is from support to support. So you're checking this one. Okay. And then the next part basically says, okay, let's say I design for the beam, like this beam. Okay. So of course you'll do the K equals M divided by BD squared FCK, right? And then like some yada 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 yada, then you find the Z, and then lastly you find the AS, right? So this 3449, right, is actually this AS. So AS required is 3449 millimeters squared. Yeah, so this is just to give you context. So the 3449 here is basically the AS you get from your beam design. Okay. Yeah, again, this is just to put some context. You actually don't need to write this down in the exam. I'm just putting it here. Okay, so that's your AS required. And then if you remember, right, let's say you have this, then we usually check the table, right? And then we get an area which is slightly higher than the AS required. So this one is we call the AS provided, which is here 3492. So this one, right, the question already gives us that. So we don't need to calculate ourselves. 3492 millimeters squared. So this is the provided AS. Okay, so from here, okay, the rest is okay. So let's go to the deflection check now, right? So for deflection check, we go to this. So we refer to this. Okay. There um we can find the actual L over D first, I guess. So let's start with that. So actual L divided by D, right, is, so L just now is given 10 meters, right? So it's 10,000. Again, this one is millimeters divided by D. So D here is also given, it's 700. So it's 700 millimeters. So again, let me get my calculator. Oh yeah. 10,000 divided by 700. So you get 14.3. Okay, there's no units because the units cancel out now, millimeters and millimeters. Okay, so that's our actual L over D. Now let's find our basic L over D. So basic L over D, right? If you refer to the formulas again, we start by finding rho 0 and rho. So let's start with rho 0 first. So okay, step 1, find rho 0. So the formula just now is 10 to the negative 3 square root of FCK. So this one is 10 to the negative 3 square root of 30. Because from just now, right? Yeah, concrete class is C30. So just plug in 30 there, then you will get 0.00548. Yes. Yep. So this one. Or you can express it in percentage also. So it will be 0.548% TTB1. So it's the same thing. Okay, that's for rho 0. Then let's go to rho, which is the reinforcement ratio. Again, for basic L over D, the area of steel that we're being used is AS required, not AS provided. It's different from the crack control. So be careful with this. So we'll get AS required, which is 3449. Again, it's from the formulas, like the bending moment design. We'll get 3449, right? 3449. And we divide it by B times D. What's B? B is 325 times 700. 325, 700. So I can make this a percentage by multiplying by 100. Okay, so let's see what we'll get. 449 divided by 325. Multiplied by 700, multiplied by 100, you get 1.52%. Okay, so if you notice, this one is bigger than 0.35%. It means that you need to use formula. Yeah, you see. So if rho is bigger than 0.35%, we need to use this very long formula. Okay, instead of just getting from the table. Okay, then we have two cases. So it depends on whether rho is bigger or smaller than the rho 0. Okay, so in this case, rho is 1.52%. So this one is definitely bigger than rho 0, which is 0.548. Okay, then we just use the formula. So basic L over D is going to be quite long, so let me prepare. So it's supposed to be K multiplied by 11 plus 1.5 square root of FCK rho 0 divided by rho. Sorry, this one is divided by rho minus rho prime plus square root of FCK divided by 12 square root of rho prime divided by rho 0. Okay, so here's the formula. This one is based on, yeah, based on this. Okay, so okay, we know rho, like we know this, we know rho 0. So we know FCK also. So what's K and what's rho prime? Okay, so for K is basically a coefficient based on the support. So if it's if it's a simply supported, K is 1. For continuous beams, it depends whether it's a thin span or interior span. Okay, then for cantilever is 0.4. Okay, so that's K. Then for rho prime, again, if you remember, right, AS have uh, AS and D refers to the tension steel. Then compression means it refers to AS prime and D prime. So in the same way, if rho is for tension, then rho prime is for compression. Okay, so anything with prime means it's compression steel. So in this case, we need to find rho prime first. So let me see. So there's given 2H16, right? And it doesn't really have. Let me see. Yeah, it doesn't really have AS required for compression steel. Let me check first. This one I'm not so sure. Sorry. Let me keep on speed part. 2 times pi r squared. Wait, okay, I'm not so sure with this. 2 times 550 equals 402. Okay, well, I don't know why they apparently don't give that, but okay, interesting. Okay, okay. Anyways, rho prime in this case is I'm referring from the tutorial solution because they don't really give the AS required here. Yeah. Hmm. Yeah, it's quite weird. Okay. So, okay, since in this question they don't really give, right? So assume AS required prime, right, for the compression steel is 254. I'm just matching the tutorial solution since they don't really give here. Okay. So rho prime is AS required prime divided by D times D times 100%. Okay, so 254 divided by the size is 325 times 700. So 325 700 times 100%. So in this case, 354 divided by 325 times 700 times 100, you'll get 0.11%. Okay, now that you have all this, right, then you can plug in the formula. Okay, so again, I'll copy this. Okay, so let's see the question again. It's an n span of a continuous beam. So for n span, K is 1.3. So 1.3 Again, this one is because it's n span. Then we multiply it by 11 plus 1.5 square root of 30. FCK is 30 just now. Then we multiply by rho 0. Rho 0 is 0.548%. You divide it by 1.52%, then minus 0.11% plus square root of FCK, which is 30 divided by 12, square root of rho prime, which is 0.11%, divided by rho 0, which is 0.548%. Okay, so you just plug in everything to your calculator and you get basic L over D. So 1.3, you multiply by 11 plus 1.5, 0.548, 1.2, plus square root of D divided by 2, square root of 0.11 divided by 0.148. You get 18.72. That's your basic L over D. So first step done. Okay. Then for second step, you'll get F1, F2, and F3. So let's start with F1. So F1 just now is, sorry, it's considering the T beams. So it's 1 minus 0.1 BF minus BW minus 1. So 1 minus 0.1. In this case, right, the B are the same because it's rectangular. So it's both 3 to 5. So it's both 3 to 5 over 3 to 5 minus 1. So if you notice, this becomes 1. So this whole thing becomes 0. Yeah, including this, it all becomes 0. So 1 minus 0 is 1. So that's our F1. And for F2, it accounts for the span. So for span, it's 7 over L. So in this case, it's 10, right? So 7 over 10 meters. So that becomes 0.7, right? Yeah, 0.7. So that's our F2. F2, you need to limit to 0.8. So use F2 equals 0.8. I'm going to show it here. Yeah, F2 is 7 over L is less than 1. Okay. Oh, sorry, 0.8 is F1. Sorry, 0.8 is F1. So this one limit to 1. Limit to 1. Sorry. So F2 you just use 0.7. Okay. Then we have F3. So for F3, you will need 3110 divided by sigma S. So let's start with sigma S first. So sigma S is sigma SU AS required divided by AS provided, and then 1 divided by delta. Okay, but sigma SU, we need to find sigma SU first. So sigma SU is 0.87 FYK SLS divided by ULS. So 0.87, just now the steel is grade 500. Then for ULS, is 1.35 GK plus 1.5 QK. Then for SLS, this one we check the question first. This one is in the office area. So if it's in the office area, oh, sorry. If it's an office area, the SLS design load is, so GK, then GK is the same, plus psi2 in office is 0.3. Then you have QK. So it's something like this. Okay, so let's go a bit down. So you get something like this. Okay, usually they will give like GK and QK, so you can just plug in the number. But in this case, since they only give this GK over QK is 2, right? So you just need to do some algebra. So if GK over QK is 2, right? Then in that case, GK is just 2 QK. So in that case, we just substitute everything. So 0.87, 500. So GK is 2 QK, right? Plus 0.3 QK divided by 1.35 times 2 QK plus 1.5 QK. So if you notice, the QK will eventually cancel everything each other. Okay, so 0.87, 500, this is 2.3 divided by 1 pound. 1.35 divided by 2 plus 1.5. You get 4.2. That's QK, QK. So you can notice this cancels out. So you will get 0.87 times 500 times 2.3 divided by 4.2. You get 238.2. So that's your sigma SU. Okay. So now you have the sigma SU. Let's go back to sigma S. So sigma SU just now is 238.2. And you have AS required. AS required just now is 3449. You have the 3492. 3449, 3492. 3449, 3492. 3449, 3492. Then you multiply by 1 divided by delta. In this case, delta is, do they give? They never give. So I guess we can use delta equals 1. Oh, no, sorry. They give. Delta is 0.9. Okay, delta is 0.9. So that's the redistribution ratio, 0.9. Okay, so that becomes 238.2 multiplied by 3449, 3492 times 1 divided by 0.9. Okay, so you get 261.4. Yeah. Okay, and then you go back to this. So it's a pretty long process. So 3110 divided by sigma s 261.4. So that is 1.186. Okay, so it's a pretty long process. But now that we have everything, we can just plug in the whole formula in this, perform the comparison. Okay, let's get our actual L over D, which is 14.3. Then we check it with the basic L over D, which is 18.72. You multiply by F1. So F1 here is 1, F2 is 0.7, F3 is 238.2. This looks sus. Wait, give me a second. Sorry, it's 1.186. There it is. Okay. So 18.72 times 1 times 0.7 times 1.186. You get 15.54. So this one is less than. Write it down. So this one is basic L over D multiplied by F1 multiplied by F2 multiplied by F3. So done. So deflection here is okay. Sorry. So it's a pretty long process. But it's actually very straightforward. So just follow the steps. Okay. For the next one, we need to check the crack control. So assume concrete cover is 30. Do they limit to any number to crack? Let me see. Okay, we can refer to this. Okay. Sorry. Wait, let me see. Oh, they limit to 0.3. Okay. Again, this one I'm just referring to a tutorial because um I don't want you to get confused because I do like one way and then the professor do the other way. Then yeah. So limiting crack to 0.3 millimeters. So again, we just refer to the table. So for the table, right? If you notice, you will need this one, sigma s. Okay. Oh, we can do the reinforcement ratio first. Oops. Okay, let's do reinforcement ratio first. Okay. Okay, so let's check the reinforcement ratio. So check reinforcement ratio. So let's find rho first. So rho in this case is 3449 and 3492. 3449. Oh, sorry, this one we use the ES provided 3492 solution. Then we use B, which is 325 and 700, right? So 325 times 700, then we multiply by 100% to make it percentage. Okay, so 3492 divided by 325 times 700 times 100, you will get 1.53%. Okay, then we check with the limits. So for this, rho is less than 4%, which is good because that's the maximum limit. The lower limit, we refer to the table. We have FCK equals to 30, right? So we just go to table. So for FCK equals 30, the minimum percentage is 0.15%. Okay, so that's our lower bound. So 0.15%. So this one is still bigger than 0.15, right? So means the ratio is okay. So that's our first step. For the second step, we need to limit crack width, let's say for 0.3 millimeters. So we can either check the spacing or we can check the bar size. So yeah, crack size is 0.3 millimeters. You can check the bar size or you can check the bar spacing. But then if you notice, the input needs the steel stress. Oh my God, sorry. So the steel stress is actually the one that we just calculated just now, sigma s. Where's sigma s? Sigma s is 261.4, right? So 261.4 is around here, somewhere around here. Oh, yeah. So we can do interpolation. Okay. 260 is roughly in the middle. So I guess I'll just take the average between the two. So I'll use the value 14 and I'll use the value 175. Okay, just because 261 is roughly in the middle. Okay, so 14 and 175. So you can pick either two. So 14 or 175. So obviously, 14, 40 and 25 is bigger than 14. Okay, so again, it's an or, it's not an and. So you either limit the bar size or you limit the spacing. Since the limiting is 14, while we have the diameter just now is 40, right? 40 and 25. So what we can do is limit the spacing into 175. So how do we calculate the spacing? So we have 40 and 25, right? So 40 and 25. So 40, 25, 25, and 40. Okay. So this is to the center. So this one, what's the limit just now? The limit is 175. Okay. This 175, 175, and 175. it basically questions whether can you fit the steel bars. So that's a question. So again, we have 40, right? So the radius is 20. And then for, let me check. So we have 40 and 25, right? 40 and 25. So 40 and 25. So 25 is 12.5, right? So what's the middle? Mm, So let's find this. So 175 minus 20 minus 12.5. So you will get 142.5. Okay. Then for this one, it's 175 minus 25, right? Because this one is half lah. So the whole thing is 25. So this is 150. This one is 142.5. So again, what I'm doing here, so I've taken the maximum bar spacing, right, which is 175. And then I just space out the bars accordingly using 175. Now we just need to check, right, if the whole um, like the whole stretch, right, is still inside 325 now. Okay. Wait, let me check. I think I made a mistake here. Wait. Give me a second. Okay, sorry for this one, right? Okay, this one I need to check again. If I say guys, but this one, right? I kind of forgot how to do this. Okay, so I'll get back to you after I find. Okay. Yeah, but anyways, so we've gotten deflection and reinforcement ratio. Sorry, this one I'm not too sure. Yeah. So yeah, this one I'll mark it after that. Yeah, because the way I remember it is a bit different. Oh my god. Okay. Anyways, let's continue the next one. Um, yeah. Okay, for this one, right? The span divided by F ratio. So again, this one is checking for deflection. I think the steps are like all very similar. So I guess I can leave it for your own practice because it's exactly the same. We just have different values of GK over QK. We have different values for delta. So when I release the document, I'll try to complete this so y'all can see the solution and compare it yourself. Yeah, but for now, y'all try to do this yourself first. Okay, because I want to discuss a little bit on Slab first. Okay, but again, this is exactly the same as this one just now. You just need to find the basic L over D, and then you need to find F1, F2, and F3. Okay. Okay. Okay, sorry. Okay, here's the appendix. This one is I just want to I just want you to know that we have some graphs. It's for deflection control, but it's basically if you read here, right, the curves are based on the following expressions. So these are the formulas that we just used just now. Okay. So if you don't like to use a formula, you can actually use the graph, but it might be a little bit confusing. So I still prefer to do the formula. Okay. But if you can see here is the FCK, is the S required divided by BD. So you just draw a line to the correct FCK, and then you just draw a line to the left. You'll get to the basic L over D. Okay, this is the basic span to effective depth ratio. Sorry. Yeah, so that's how you get the basic L over D if you want to use the graph. But I still prefer to use the formula. Okay. This one, still stress, is actually sigma SU. So again, we use this for F3 and also for crack control. So for this one, again, you need to find the ratio between GK and QK. And then you just draw a line to the correct, what's it called? To the correct side tube, and this one is what's it called? The partial factor of G, the partial factors of the dead load. So you just draw a straight line up and go to the left. You get the sigma SU. Again, this one I still prefer to use the formula, but I'm just showing you here just in case that okay, I see this in tutorial or lecture, but then I don't know what this is. But this graph is basically this formula. So you don't need too much to worry. You don't need to worry too much. Okay. Okay. With that said, I hope you can do the deflection check. Actually, deflection check is way more important than crack control. Although crack control also you need to limit it. Okay. But my emphasis on today is actually the deflection check. Okay. For next one, let's do the slabs. Okay. For slabs, again for today I'll just do the introduction only. So if you haven't known, slabs transfer load to beams and columns. So let's say this is your slab, you have a person standing. The load basically will be transferred by the slab, and then into the beams and columns. It goes downwards basically. Then if you have a beam here, yeah, then it goes to the beam first. Okay, so slab is basically your first element that gets loaded, you can say. Okay, slab design is very similar to beam. You can even say that it's quite identical, like the steps. You will actually use the same formulas as your first quiz, your beam design for slabs, but they have extra steps, which depends on the slab type. Okay, so that's why we need to understand the types of slabs first. Okay, so here's the types of slabs. So we can differentiate slabs based on the continuity, supporting structures, or load transfer direction. Okay, for continuity, there are two types. It can be simply supported, it can be continuous. Differentiating this is important for the moment redistribution. So this one is actually uh, quite similar to your beam. So let's say you have a simply supported slab, then you expect the bending moment diagram to be just simply like this. Just go down and then like this. Okay, that's the simply supported slab. And then the maximum moment is WL squared L, just in case you haven't known, if it's uniformly loaded. So this one is, let's say this one is W. Then the maximum moment is WL squared divided by 8. Okay, so that's for simply supported. For continuous slab, then your bending moment diagram is, I think you can expect, it's very similar to the beam. It will be something like this. So this is your moment, this is your X. Okay. So yeah, so if you notice from the bending moment diagram, right, you know if it's a continuous slab, moment redistribution can happen. Okay. So again, this is depending on the question or depending on your assumption, like how much is the redistribution. Okay. So that's the importance of sorry, differentiating slabs based on continuity. Okay. The next one is differentiating slabs based on supporting structures. So there are actually three types of slabs. First one is slabs on beams or walls. So these are the solid slabs. So if you notice that the slab is supported by these beams. Then we have a rib or waffle slabs. So basically you have like one whole slab and then it's just like have a lot of waffle, or like waffle shape protrusions. Okay. Lastly, you have the flat slab. So it's just a whole slab supported on columns, and there are like no beams. Okay, so these three slabs, they have different ways to design. Okay, but for this course, we will only focus on solid slabs or slabs on beams. So this one is for CV3011. I don't know if they will teach the other two in advanced RC design, but I know it's used in consultancy firms. Okay, but in CV3011, we'll just deal with solid slabs. Okay, so first one is important for moment redistribution. Second one is important for design steps. But again, we will only care about solid slabs for this course. So yeah, this one is not that important. The second one for this course. Now the third one is very important for this course. So this one is the load transfer direction for solid slabs. Okay, slabs can be one-way spanning. It can be two-way spanning. So one-way span, it means, okay, let's say you have a slab here, right? This is your slab. This is your person, right? Let's say that's the load. Then these are your beams, these are your columns. Okay, it means, okay, let's say you load this whole slab, right? The most of the load will go to the long side of the slab. Okay, because like this side is quite short, like you can see. So we can assume that all the load will only go to these two beams or these two sides. That's what we call the one-way spanning slab. Okay, so in this case, you can see that this is the top view. So it basically means that the load will be distributed this way to the beams. Okay. Okay, then so there are a few types of slabs also. There's like slabs supported on opposite edges. So if you see here is a free edge, right? So it means let's say you were seeing the underside of the slab, right? Okay, let's say this is your underside of the slab. Okay, let's say this is your slab. So it means that this side is supported by a beam. Then this side is also supported by a beam. As a reference, that's the person on top. Okay. But these two sides are not supported by beams. So we call this the beam edge. So this one is the low view, view from below like this. So your beams are only located in two sides only. So these are beams. Okay, in that case, the load will be distributed onto the beams. So that's what this means. Since these two lines are free edges, it means that it has no beams on the sides. So the load must be transferred to these two beams for this slab. Okay, it will transfer to these two beams. Then for this slab, it will transfer to these two beams. Okay, sorry. So slab supported on like opposite edges, it will be confirmed a one-way slab because it can only support load onto the two beams. Okay. Now let's see to the slabs with beams all around. So instead of like having like two beams only, right? Now the slab, right? Okay, let's say this is your view from below. Okay, again, this is your person as reference on the top. So the slab is supported here, here, how to draw? Here and here. So it's supported on these four sides. So these are your beams, let's say. Okay. Again, this is the underside. Okay, let's say your slab is supported in these four corners, these four sides. Then in this case, it can be one-way spanning, it can be two-way spanning as well. So how do you differentiate it, right? It's by the ratio of the lengths. If the slab is like very slender, very long enough, like this slab right here, it's one-way spanning. So this is L1, this is Lx. So this one is L1, this one is Lx. Sorry. So if you notice, right, by intuition, the load will be distributed between these two beams because the aspect ratio is very long. Okay, so it will transfer the load onto the longer beams. It's unlikely for, okay, let's say you have a person here in the middle. It's unlikely for the weight of the person that will be transferred to this beam. It's very unlikely. Most likely, the weight of the person will be transferred to these two beams. Okay. While in this case, if you see this slab, let's say I have a person in the middle, right? Then the load can be transferred here, can be transferred here, here, or here. Okay, because the slab is quite square, you can see. So that's why it depends on the aspect ratio. So if Ly is bigger than Lx, sorry, if Ly is twice the length of Lx, then the slab will be like very long like this. Okay, then it will be one-way spanning. But if the Ly and Lx is like square-ish, then it will be two-way spanning. Something like this. Okay. So that's how you differentiate like a one-way spanning and two-way spanning. Okay. Sorry. The way you design one-way and two-way spanning, right, is actually quite similar. But for two-way spanning, they have like extra steps in the beginning. So that one I will not cover today. So today I will just cover the one-way spanning slab first. Okay, let's start with the moment redistribution. So I hope you still remember. Okay, but before that, again, if you design a slab, right, it's quite similar to beams. So slab design, right, you design it as beams, but with a width of 1 meters. So what I mean, right? So let's say this is your slab. You can imagine just taking like 1 meter portion of it. Because slab, right, usually is very long. Okay, slab is usually very wide, very long. So we just assume per meter. Okay, just assume 1 meter of the slab and we treat it as a beam. Okay, so if you see the side view of the slab, of this slab, right, please, it will look something like this, right? So these are your three supports. Okay, so something like this. Okay, and then if you take like 1 meter of the slab, right, it will sideways, it will look something like this. Wait. So if you notice here, right, we have a sort of beam, you can say. So the 1 meter here, right, is actually the 1 meter here. And when you look at this shape, right, it really looks like a beam, right? It will look like a beam. So something like this, the bending moment. Okay. So yeah, the bending moment will look something like this for this slab slash beam. Then for this one, again, we have 1, 2, 3, 5 supports. Okay. So the bending moment will look something like this moment, right? Something like this. Okay. Again, this one we treat it as a 1 meter beam. Something like this. So this one is 1 meter. So if you see the cross section, right, it will look something like this. So this one is 1 meter. So well, I'm talking about this one, like this side. If you see it, it will 1 meter, and then you have some dots here. That's your reinforcement. Okay. So yeah, here I'm just like emphasizing that slab design, right? You can treat it as a beam, but the beam has a width of 1 meter or 1000 millimeters, same thing. And then the design steps, right, later will be exactly the same. Okay, it's just the design step is exactly like a beam, but you treat the width to be 1000 millimeters. Okay. Okay. So again, let's go back to moment distribution. I've been like jumping around a little bit. Okay, for moment distribution, let's review first. So let's say you have like delta equals 0.85, right? So what we will usually do, right, in the beam, so we have like the hogging decrease, right? So we have 400 times 0.8, sorry, 15%. 350 times 15%. So what's that? 60 and 52.5. Sorry. Okay, and then usually what we do, right? After we get the hogging decrease, we will draw a diagram, which is like the decrease of the moment. So moment decrease or increase. Okay, so again, in the leftmost side, the redistribution is 0 because the moment is 0. Then here, the redistribution is 60, again from 60 here. Then 350 is 52.5. Then this one is 0. So you draw a straight line, something like this. Right? So this one again, just review. Now here's the difference. Okay. So back in the day, we assume that 200, right? We just take the middle. So in this case, this one is 30. This one is basically your average between 60 and 52.5, which is 56.25. This one is 26.25. Okay, so this one is your the way that you usually do it. Then in the end, right, yes, 200 plus 330, 300 plus this, 250 plus this. Okay, so this method, it assumes, so this one, it assumes the sagging moment, sorry, the maximum sagging moment is exactly in the middle of the span. So what it means, right, if you see here, right, so 400 corresponds to 60. The 200 here, right, if you notice, it's not exactly in the middle between like these two lines. Okay, so the previous professor, he assumes that 200 is like roughly in the middle. So that's why we just take half. So 30 in this case. So 200 plus 30 is 230. But in actuality, the sagging moment is slightly to the left or slightly to the right, correct? So the same as this one, if you notice here, right? Yeah, it's not exactly in the middle. So if you want to be like very, very accurate, you need to find the, basically you need to find the distance. You need to find this. So what's x here? So if you want to be accurate, and then we just take the value here. Okay. So I hope you understand. So the one that we've been doing, we assume that the sagging is exactly in the middle. Sorry. See, the method above assumes that the sagging moment lies exactly in the middle of the span. Well, it's usually not the case, which I just represented just now. So it's basically something like this. It's not exactly in the middle. Even this one, right, it's not exactly in the middle. So if you notice here, right, it's slightly off. Okay, but it's a good approximation. Okay, but for the second prof, he wants it to be accurate. Okay, so I'll explain how you get this x. Okay, basically the distance, so you can find the ratio. Okay, and you can find the decrease basically. Okay, so I'll just directly straight to the I'll give you example directly. So if concrete slab 200 millimeters thick, then you have the spans of 6 meters and 4 meters. Then you have the loads, and then now here's the important thing. Based on a single load case arrangement, the design moment at the 1 meter strip of slab is assumed to be 46.6 kilonewton at the internal support before redistribution. Okay. Oh, sorry. I won't go into the design today. I'm just explaining the moment redistribution for one-way continuous slab for today. Okay. Okay. So this is your slab. Okay. Again, we assume it's a 1 meter slab. So it's actually, if you see it in 3D, it's actually like this. So this one is 1 meter. Okay. I guess I can leave it like this. Okay. Okay. Just to give you some context. Okay. So first things first, right? The bending moment diagram of this slab will look something like this. Right? It will look something like this. Okay, similar to our beam. Okay, but then we need to read the design moment 1 meter strip of slab is obtained at 46.6 kilonewton meters at the internal support before redistribution. It means that internal support means this one, right? So it means this moment is 46.6 kilonewtons meter. Okay, so let's say you want to design for the again 6 meter span, right? So you need to find the moment here, correct? You need to find the moment here, and you need to find the moment after redistribution somehow. Okay. So again, for this one, we cannot just simply use the we cannot just simply use this technique. Okay. We need to do another technique. So in this case, I've written here on the first line. It's more accurate to refer to the shear force diagram when redistributing the moment. So instead of taking half, you actually need to refer to the actual shear force diagram. Okay. So how do you do it? First things first, you can do some free body diagram. Okay. So imagine cutting the beam, sorry, cutting the slab here. Okay. Imagine cutting the slab here. So cut here. So what you will have, right, is so you have the slab like this. Then you have two supports. So let's say this is AY, this is BY. Then you cut here, right? You have the 46.6. Okay. At the support, the moment will be hogging. So hogging moment is actually like this. This one is 46.6, right? Sorry. It is 46.6. So again, it's from the BMD. Next one, you have the distributed loading. So you have a distributed loading here. Let me make the colors different. Okay. So what's the distributed loading? We need to refer to the loadings. Or they give the variable loading and the finishes. Okay, so W is 1.35 GK plus 1.5 QK. So in this case, 1.35 multiplied by, you have the self weight of the concrete. So again, concrete is 35 kilonewtons per meter cube, right? So 25, you multiply by the area, which is 1 meters multiplied by what's each? 200 millimeters. It's 200 millimeters. So it's basically 1 times 0.2 plus finishes is 1.5. Yeah, correct. Kilonewtons per meter square, but then we just assume it's 1 meter. So it's 1.5. Then we plus by 1.5 multiplied by QK. QK here is 3 kilonewtons per meter square. So 3. Let me put this down. Okay, something like this. So in the end, you get W is what? 1.35. 25 times 1 times 0.2 plus 1.5. You get 13.28 kilonewtons per meter. So that's your loading. So this one is 13.28 kilonewtons per meter squared. So what you do next, right? You need to find the shear force diagram. But before you can find the shear force diagram, you need to find the reaction forces first. Okay, so I'll label it as A, is B. So I can take moment, let's say about A. So moment about A is you have a few forces here. What's the span? Oh, the span is 6 meters. 6 meters. So again, you have the distributed loading, which acts in the middle, right? So it's 13.28.6. So that's 79. Okay, so the moment at A, right, is 79.7. You multiply by 3 because it's half of 6, right? So you're taking this moment as negative value. Okay, then you have this moment, so plus dy times 6. Then you have this couple moment, which is minus 46.6 equals to 0. Okay, so this is your MOM now, basically. So you just need to take moment. Then dy is 79.7 plus 46.6 divided by 6. You get 47.6 kilonewtons. And then you can take the sum of Fy, sum of vertical forces. So you have Ay going up, you have 79.7 going down, you have dy going up. Okay, so Ay is just 79.7 minus dy. So that's 32.1. So okay, this is your MOM. Okay. Next one, we need to find the shear force diagram. Okay, so let's say this is your slab shear force in kilonewtons. This one is meters. Okay, first things first, you have AY, right? So you have AY going up. So the shear force diagram, right? For the one that forgot, right? Your shear force diagram should start and end at 0. Okay, because 0 means equilibrium. So you will start at 0, right? Next one, you have the AY. AY jumping up by 32.1. So from 0, you will jump up to 32.1. Okay. Next one, you have a uniformly distributed load. So if the load is constant, then the shear will be a slope. Okay. It goes down by 79.7. So this thing will go down by 79.7. So 32.1 minus 79.7 is negative 47.6. Okay. And then lastly, you have another force here, By. So By is pointing up, so 47.6. So it goes back to 0. So that means your shear force diagram is correct. Okay. You can actually draw the bending moment diagram, but in this case I won't. Okay. Because it's not really important, I guess. Okay. Oh, actually, I'll just show you that. That's why not. Okay. You don't need the second part, the bending moment diagram. I'm just showing here. Okay, if you remember from your MOM, the area of your shear force diagram is your moment. Oh, sorry. Okay, first things first, we need to find the area of this triangle, but we cannot lie because we need the distance first. So we need to find the distance first. So in this case, the distance is 6 meters. So this one is 6 meters. Oh shoot, I made a mistake. Oh man. If I say, okay, sorry, 46.6, right? Is the bending moment before redistribution. Okay. So if you want a redistribution, is it given here how much? No, right? Oh my gosh. Okay, let's say delta is 0.85 or 15% redistribution, right? Okay, in this case, you don't use 46.6. You use 46.6, you multiply by 0.85, which is the 15% redistribution. Okay, in this case, it's 39.61. So here is 39.61. Okay, oops, this is my blunder. Okay, so okay, my values are a bit off. So this one should be 39.61. So this one is not correct value. Okay, let me recalculate 39.61 plus 79.7 times 3 divided by 6. So you get 46.45 here. Where you get everyone to be 33.2. Here, let me correct the values first. It is 33.2. This one is 46.45. Yeah, anyways, let's go back to the one that we were doing before. So the whole span is 6 meters, right? So this one is whole thing 6 meters. So if you want to find this distance, you just use similar triangles. Okay. So let's say I label this as x. So by using similar triangles, so x divided by 33.2 is equals to, then I'll take this whole triangle, this whole thing. Okay, so this whole triangle. Okay, so that's 6 meters divided by 33.2 plus 46.45. In this case, you get x equals to 2.5 meters. Okay, so now you get x to be 2.5 meters. Okay, again, let's go back to our bending moment diagram. So in this case, what our moment is the area of triangle, right? So area of triangle is half times base times height. So that's 41.5. Then something else to take note, right? In this course, we assume moment positive to be below. This one is compression side. So positive is below. So actually, this is a moment increase. It looks going down, but it's actually a moment increase. So it goes to 41.5. Okay, and then you have to decrease, which is this area. So it's half times 6 minus 2.5 times height, which is 46.55. Really, really clear. 81.285. So this thing will decrease again. It's because it's negative, right? It will decrease by 81.28 by this much. So 41.5 minus that, it becomes negative 39.7. 39.8. So this one minus this. Okay, so it will become like this. So which is expected lah, because 39 points. Okay, it's just what's called assumption error. What rounding error, rounding error. Okay, so it's correct lah. So because the shape, right? Because we're taking this shape, we're taking like this half. Okay. So now if you see here, right, when you want to design for the sagging moment of the beam of the slab, I mean, you'll take this value, which is 41.5. So you can actually just use this if you want. So you don't need to draw the bending moment diagram. But if you want, yeah, you can. This one is enough if you want. Okay, so if you're designing for, if you're designing for the moment, right? So this one is your MED or M, this is your M for design. Again. Okay. Yeah. So I think that's all for today. I think I messed up a lot today. But I hope you'll get what I'm saying. Okay. First things first, right? I covered deflection already. So deflection is just basic L over D times the three factors F1, F2, F3. And then you compare it with the actual length to depth ratio. Okay, so just this comparison. For crack control, you have reinforcement ratio. So this one is also pretty straightforward. So your rho must be between the minimum rho and the maximum rho. For this one, I'm not really sure, so I'll get back to you as I know. Okay. This one is exactly the same. Then for slabs, I've covered like the types of slabs and what differentiates like one-way spanning and two-way spanning. I've covered like the redistribution, the difference between like the old method and the new method. Okay, the new method is more accurate because it actually finds the distance. Okay, so if you remember this x, right, is actually the one that we just found now, this one. Okay, so again, if you notice 2.5 meters is not really in the middle of 6 meters, right? The middle of 6 is around here, which is 3 meters. Yeah, but then if you want to find x, right, you need to find the shear force diagram. How do you find the shear force diagram? You need to cut the beam, cut the slab. So cut in the middle, then you find the moment, right? Sorry, you are given the moment. So you can do some MOM stuff, which is basically your force and moment equilibrium. Okay, then you draw the shear force diagram, then you find the maximum moment. So it's a lot more steps because it's more accurate. Yeah, but I think that's all for today. Next week is recess week, so I won't be any I won't be having like any sessions. So the next session is 2 more weeks. Okay, so the next session will be in 8th of October. So next week no session. Okay, so have a nice recess week. Yeah, for today is just this one. Okay, so I'll stop the recording. Are there like any questions? Today I think I'm jumping quite a lot. Let me stop the recording now.